Welcome to our first video on digital design for the class. What our goal here is to start kind of talking about what a digital system is, which is basically foundation of computer systems. Computer system is just a digital system. And we're going to start at the very bottom talking about kind of the foundation of computers, which is transistors. Which transistors are basically an electronic switch that allows us to create zeros and ones, which are the basis of the binary language, or the two value system used throughout the computer system, throughout all computers and digital systems. So what we're going to do, let's go ahead and get started with first kind of talking about how a signal goes from an analog world to a digital world. Analog is basically everything you see in the world where things they're not either on or off or 0 or 1 like a binary system, but they have a continuous value. For example, here is an analog signal. It goes all over the place from some value to some higher value and moves up and down. This one is actually a representative of a heartbeat. That's a signal that comes from actual heartbeat there. Now, if you want to turn it into digital so you can count how many heartbeats you have, you got to somehow decide when this signal will be 1, when this signal will be a 0. And what they've decided in the past is they draw two lines. They draw a line, we call it Vmax, another line, we're going to call it Vmin, and what they do is basically says anything above Vmax, we're going to call high, 1, true, those kinds of stuff. Anything so up here, so any voltage value they see, computer sees, or the transistor sees above this value, it's going to be referred to as high or 1. Anything below this would be the binary value 0. Okay, so since computers work on those two system values, those are important. You have many names for it. For example, high, this one should be sometimes called high, sometimes called true. Here's the three names, I suppose. 1, high, true, and then and also they might also use the word on to refer to a high. You can also, for the low, if there's an equivalent naming scheme where they might call it low, they might call it false or off. So those would be the names. So any voltage less than this voltage will be referred to as that. So now we got basically a transistor that by opening and closing allows us to indicate 0 and 1. And we can kind of use these limits to take an analog signal and translate it to digital system. As you see, when we go to a digital system, we lose all these details that are available in the analog details, such as this signal kind of moving up and down in here. We won't necessarily see these up and down. All we see is when it goes above this line, it goes to 1. When it's below below this line, it goes to 0. And then back up. But if let's say, for example, this is a heartbeat, and I'm only trying to count the number of pulses because I want to know what my pulse is, this is good enough. I don't need all those details. On the other hand, if I'm a cardiologist trying to figure out if the person is having a healthy heart or not, I need to be able to see all those signals. So depending on what your application is, sometimes digital loses some information. But for most of the things we do today, we've learned that we can go to digital and preserve what we need. Yes, it's not precisely what the analog signal was, but it's close enough for us to draw a conclusion and use the information to do what we need to do. So that's the difference between analog. So analog value, let's say this for a regular system, our limits are, the Vmax is usually set around, let's say 3.7-ish or 3.5, let's say, somewhere in that range. And Vmin is typically set around 0.7, 0.8, 0.9. And so anything below is called 0, anything above is called 1. And anything in here really is an unknown zone. So if you're 0, you stay 0. If you're 1, you stay 1. When you're in that middle range, you have to cross this line and this line before your value changes. So, and then in analog world, we have all the values. Values are continuous. So you can have 0 volt, 0.1 volt, 0.2 volt, 0.3 volts, on and on to whatever fraction you want. But in digital world, we either have on or off, 1 or 0, high or low, and that's true or false. And those are the only thing we have to work with. Okay, so that's basically it. And of course, digital systems have come a long way in assisting humanity in organizing information, retrieving information, and more they're being used in many, many different ways to help us. But the foundation of them resides in this idea of being able to take the real world information that is analog, translate it to a representation in ones and zeros, and then save it, manipulate it, and use it to make decisions. Okay. So that's what we're embarking on. We're embarking on, now that we know the working binary system, can we build our own devices that start to make decisions, and that's where we're headed. Okay. So before we go there, just a real quick visit to the transistors. Transistors are basically switches. Okay, switches such that you put a little bit of electricity at the driver portion. In this case, would be a base. This is either close. So if you put any kind of current or voltage, voltage from the base to the emitter, so there's a current flowing in here, this switch will close. This will close. So collector will close to the connects to the emitter. So these two would be close together. And then if you come back around and basically remove this, then this will open up. So there's no connection between collector. And that's basically how a transistor works. And that's the foundation of computers, because now we can basically connect a transistor to 5 volts and connect the other side to ground. So and start looking at here, when the switch is connected to ground, you get a 0. When the switch is open, you get a high. So that's how we generate high and low inside a computer, so we can keep track of the binary number. So transistors are the foundation. Initially, they were a technology called bipolar transistors. Those are or TTL sometimes referred to it. And those were kind of the beginning of technology we use. Recently, if you look at today's computer, pretty much all of them are based on complementary metal oxide technology, or CMOS. The reason they like CMOS technology over bipolar is that it uses significantly less power than the previous version of the chips. Now, this becomes really important, but you realize that today's processors, today's computer chips, are basically using billions, with the B, billions of transistors. So today's computers use billions of transistors. So if we can save power in each one of them, even if it's a very minute amount, when you multiply it by 10 to the power of 9, which is billions, it would be a significant amount of power. Right now, power dissipation and heat is the biggest reason we don't have faster and larger computers. That's the limiting factor in our ability to produce computers. So anything that we can do to reduce power consumption, it goes a long ways in allowing us to have more powerful computers. Okay, so that's this video was meant to be more of an introductory, kind of show you how we take as electrical signal in an analog world that's continuous and turn it into a digital, which is discrete. So you only have zeros and ones. And then we talked about the foundation of computer switches, which is a kind of a transistor. Here's a model of a basic transistor. And this is the bipolar transistor. Today's computer pretty much uses CMOS. So that's kind of a summary of what we have talked about. That's all for today. And thanks for watching.